the smallest number are the natural numbers. And they're called natural numbers because they're the numbers that you naturally use. You start, when you count things, you don't start at 0 and then go 1, 2. You start like I have 1, I have 2, 3, 4, 5. So they're also known as the counting numbers or the natural numbers. They're infinite, but they start at 1 and then go on forever. Then you have the whole numbers. Okay, now whole numbers are exactly like natural numbers except they start at 0. So there are 0, 1, 2, 3, 4, 5, 6, 7, 8 and stuff forever. Now in here there are no fractions, there are no decimals. Okay, these are just solid single numbers. Okay, the symbol for natural numbers is an N, either bolded, or if you can't bold, you cross it like that, to where this N has two sides. The symbol for whole numbers is a W, bolded, or a W with this extra little line right there. Next you have integers. Okay. And integers are all of the negatives, 0, and all of the positives. And so whereas natural numbers and whole numbers go on forever but only in one direction, integers go on forever in two directions. So everything that's positive and everything that's negative, but it's still no fractions, no decimals. The symbol for integers is a Z because they used I for something else. And so it's either a Z that's bold or a Z like this, where it looks like there's two Z's connected. So if you look, natural numbers go 1, 2, 3, 4, 5. Whole numbers add 0. So the natural numbers fit inside the whole numbers. And then the integers add the negatives. So both of those fit inside the integers. And then all of those fit inside rational numbers. Okay, which is a Q. Either with a line in it or bolded. And the rational numbers, it's easier to write a description than to actually write down an example of the numbers. So it's all the integers. It's all fractions. Okay. All perfect roots. Okay, and roots are, you know, like square roots. And then all decimals that end or repeat. I'm running out of space. Sorry about that. So it's all of these numbers, right? All the positives and negatives. It's also all of the positive and negative fractions. And it's every decimal that ends or repeats. So like 0.25 that ends. Or 0.222222222 forever that repeats, or 23, 23, 23, 23. What it is not is like a number like pi, 3.14, but it's 3.14 and then it keeps going forever. There's no pattern that they've ever been able to find, and they've gone out hundreds of thousands of digits on with computers. Yeah. So there's no pattern, and so it doesn't repeat, and it never ends. So that would not be rational. Okay. Well, that's where we come over here. So see how these all fit together nicely? These are like the pretty Russian nesting dolls that all lock in together. It's a nice, happy family. Okay. Numbers are all part of a family. Over here, you have like your weird cousin. Right? Or your crazy uncle, or you know how every family has one that's just sort of like they're part of the family, but they're over there. Okay, and that is the irrational numbers. Okay? And they don't fit in to this doll. Like, they don't fit inside of any of these. And with irrational numbers, you get non-ending or non-terminating and non-repeating decimals. So like pi. You also get not perfect square roots, like the square root of 2. 2 is not a perfect square, so you get an irrational answer if you take the square root of 2, because it's a non-ending, non-repeating decimal. Okay. And all of these are part of the real number family. Okay, real numbers is an R, either like with a double like that or bold. Hold on a second. Okay, and then irrational here is either going to be a bold I or like a double, but that's kind of confusing. Usually it's just bolded. Okay. So again, irrational numbers are all part of the real number family. They're still real. But they're the crazy cousin, the weirdo family member that is part of your family and you love them, but they don't really fit exactly. So in identifying numbers, some of them are easy, some of them we need to do something with first. Okay? So here, -4. Well, if we look, negative, the smallest it can possibly be is an integer, right? It cannot be a whole number or a natural number because there are no negatives there. So we start with the smallest, which is an integer, and go ahead and just write the letter. You don't have to write out the word. But if it's an integer, it's also rational and it's also real. Because that's what happens as you move up. You've got integers and then rational and then real. Yeah. For now, just to go over it. Okay, the square root of 16. Can I take the square root of 16? Mm-hmm. Yeah. That equals, what am I, equals 4, right? And 4, well, we can count up to 4, right? So it's natural. That's the smallest it fits into. It's natural. So this one's natural, and it's a whole number, and it's an integer, and it's rational, and it's real. Okay. Now on like a test or something, I wouldn't make you list all of them. I just have you maybe list the smallest one that it fits into, but I just want to go over the fact that they fit into all of these just for the notes purposes. Square root of 2. It's not a perfect square, right? So if it's not a perfect square, it's irrational. But it's also still real. So it's irrational because it's not a perfect square, and anything that's not a perfect square that's a square root is going to give us an irrational number. Okay. 24 divided by 6 is 4. I didn't mean to do that. We have 2 4s here. So if this 4 is all of these, what is this 4? The same. So you can just write the same if you want. Um, 3/4. This fraction. So if we look at this, the smallest, there's no fractions in any of these, right? So the smallest one it can be is rational. So it's rational and it's real. Seven. Well, it's a whole number because we can count to it, or sorry, not a whole. I mean, it is a whole, but it's a natural number because we can count to it, and it's a whole number, and it's an integer, and it's rational, and it's real. I knew I changed this. Okay. Pi. Irrational. And then on your paper, you guys have 3.75, which is a decimal, which makes it rational. So it'll be rational and real. So you're going to get a Q and an R. Okay, I'm going to write down the steps. So you count the digits. All right, so here I have 2 digits, 1, 2, right? And then step 3 is to reduce. Okay, so that might not make sense right now, but you count the digits. So here on 0.75, I have 1, 2 digits. I'm going to put a 75 in the numerator, and I have 2 digits, so I need 2 zeros. So I have 75 over 100. If I have 3 digits, like here, 368, I have 3 zeros. 1 digit gives me 1 0. 4 digits gives me 4 zeros. After that, then we reduce 75 and 100. Okay, so if you remember reducing or simplifying fractions, you divide the numerator and the denominator by the same thing, right? So I can divide both of these by 5, or I can divide them by 25. And it doesn't matter. If you want to divide by 5, you can. You just have more steps. You divide by 5, and then you'd have to divide by 5 again. So that gives me 3/4. Now, if you want to check it to make sure you're correct, if I do 3 divided by 4, and I plugged that into, say, a calculator real fast or something, it gives me 0.75. So I know I was right. So, checked. That's just in case you want to check yourself. 368 and 1,000. Okay, all right, so these are both even. That's the easiest one. They're both even. It'll divide by 2. Which is going to give me 184 over 500, which are still both even. So I can divide by 2 again, which is going to give me 92 over 250, which I can divide by 2, which is going to give me 446 over 125. Right, 46. Okay. And that's done.
Geez, that's a lot of work.
Yeah.
I mean, not that much work.
I could have divided by 8. Did I do that right? 1, 16, 8, 500. 1, 2. Yeah, I could have divided by 8, but see, again, you'd have to have known the rule to that. Here, I'm going to just do this to make it a little easier. Okay, 5/10. 5 and 10 will both divide by 5. So that's going to give me 1/2. And 3225 and 10,000 will both divide by 25. They'll also divide by 5, but I'm going to go bigger, 25. And that's going to be 1. I hate doing this in my head. Sorry. Okay, and then these don't divide by the same thing, so we're done there. Okay, divisibility is the ability to divide evenly by something, okay? So if we're talking about divisibility rules, we're talking about, you know, the ability of something to divide evenly by a certain number. Okay. All right, so to divide evenly by 2, any number that's even, so if it ends in 0, 2, 4, 6, or 8, it will divide by 2. Okay. The rule for 3 is you add up the digits. Okay, so you add up the digits of the number you're trying to decide if it divides by 3 or not. If that number that you get when you add up the digits will divide by 3, then the original number divides by 3. So just as an example, if I take 129, okay, and I want to know, does this divide by 3? I add 1 plus 2 plus 9, which is 12. 12 does divide by 3, so 129 will divide evenly by 3. And if I do that problem, it's 43. So I added these digits up. So if I did, like, say 139, that would have given me 13. So then 139 does not divide evenly by 3. Okay, so that's just, rather than having to take the time to divide, especially like a larger number by 3, this is just a quick way to see if it even will. The rule for 4 is if the last 2 digits divide by 4. Then the whole number will divide by 4. Okay, so if I have, like, say 3, 4, 6, 9, 2, 4, and I want to know, does this big giant number divide by 4? Right here. 24 divides by 4. So because 24 divides by 4, this whole thing will divide evenly by 4. And if I actually do that math, see, even. Okay, so that's a way you can tell if it'll divide by 4. You just take those last 2 digits and see. Do those divide by 4? For 5, if it ends in a 0 or 5, it will divide by 5. For 6, the rule is if it'll divide by 2 and 3. Okay, so you check both of these rules. You see if it's even, And then you see if the digits add up to something that divides by 3. So if it fits for both of these rules, it'll divide by 6.
Divides by 2 and 3 or 2
2
or 3?
and 3. It has to be both, because 6 is 2 times 3, right?
Yeah.
So it has to be that it divides by both 2 and 3. Okay, there's a rule for 7, but the rule for 7 is so complicated that it's easier to just divide by 7 and see if it works. Mathematicians did come up with a rule to see if they could. Kind of like 4, except a little bit more. It's if the last 3 digits divide by 8. A lot of times, though, this one's kind of useless because how many of you have memorized all the 3-digit numbers that divide by 8? But if you have a really big long number, it's easier to try to divide the 3-digit number by 8 than the big long number by 8 just to check it. 9 is kind of like 3. Divides by. If. So 9 is like 3. You add up all the sum of the digits, and if the sum divides by 9, then the whole thing will divide by 9. So 3816. If I add that together, I get 18. 18 divides by 9, so 3,816 will divide by 9. And then 10 is the easiest one. Ends in 0.